Here's where we left off last time, right? We've got, if we have some differential equation, remember, that's just an equation that involves derivatives, and the way we solve a differential equation is by undoing the derivatives, right? We want to find, it's calculus jeopardy, right? We want to find the function we would differentiate to get this, okay? And so we represent that. Our new notation is we're going to use integral notation, right? And so we've got the integral of whatever's inside is what we're playing calculus jeopardy with, right? That's what we're trying to take an antiderivative of. Okay, this is the integral sign. This is what we call the integrand. If I go back a little bit, where's our, back a long ways, I guess, right here. So there's our integrand, right? We're taking the antiderivative of. It's always pinched between the integral sign and then d something, the variable of integration. Usually it's going to be x's or t's or something like that. Then the answer we get, we're going to get the antiderivative, right? The answer to the calculus jeopardy, plus some constant of integration, and we call that a general solution, right? So if we apply that to this situation, the antiderivative of 2x minus 1 is x squared minus x, right, is what we get. That with the different derivative of x squared is 2x, the derivative of x is 1, and then we have to include our constant of integration, right, which is, that doesn't look very capital, but it's always written in a capital C for calculus. Okay, so that's a general solution, but if we're given some additional information, if we look at what the graph of a general solution would look like, remember, it's an infinite family of curves. So for every value of c that we choose, that's going to correspond to a trajectory of that family of curves, right? Now the thing is, all of those, if I take any one of those curves and I ask what the derivative of that trajectory is at x equals 1, I'm always going to get the same answer though, right? When I differentiate these, I always get back the same slope, okay? But if we want to pin it down to, so they all work, right? They're all viable answers to my differential equation. But if I want to get one specific trajectory, I have to specify something that's going to pin that trajectory down. And that usually is going to end up being a point through which that trajectory passes, right? So in this case, we know that it passes through the point 1, 1. And think what that means. That means that when x is 1, the value of the function is 1. So we could show it as a point on a graph. We could equally well write that by saying this. We could say something like, whoops, we could write that like f of 1 equals 1, right? That means the same thing as that point, okay? Now what's that do for us? Well, that allows us to go back and solve for the specific value of c, right? If I plug 1 in for x and 1 in for y, I get the solution c equals 1. And so for that condition, we end up with a particular solution, right? A specific solution, which in calculus we call a particular solution, and it's going to be that one trajectory. So that's the equation of that one curve that passes through the point that we specified. Okay. So on the assignment, you were given something. Was it u? Is that what the function was?
Yeah.
Like u as a function of x, and they told you something like u of 1 equals 7 or something like that, right? They told you something specific. Same deal. Instead of an f, it's a u. But you're going to do the same thing. You're going to plug in those values. Once you get the general solution, you're going to use that specific information to plug in values for x and y so you can solve for the value of the constant. Okay? All right, so what about one like this then? Okay, this is what we call a second order differential equation, because it's not just the first derivative, it's a second derivative, right? So in this case, we're told that the second derivative is equal to x squared, okay? So what would I do to find the first derivative? Okay, I'm going to anti-differentiate, right? That function, I'm going to, the antiderivative of the second derivative is the first derivative, right? So we would know that f of x, or f prime of x, sorry, is going to equal the integral, or the antiderivative, whatever you want to call it, of this. Okay? And so playing calculus Jeopardy, or better yet, we came up with the generalized power rule, right? That's a pretty important one. You fill in the blanks for me here. If we've got the antiderivative of u to the n du, what's my answer? It could be x instead of the u, doesn't matter.
Use the n plus 1 over n plus 1. What's the u?
U is whatever we're taking the derivative of. In this case, it's an x. Well, that's the variable of integration, right? So that's the integrand, that's the integral sign, that's the variable of integration. And the part that we're interested in is always the part that's between the integral sign and the whatever it is that we're differentiating with respect to there, right? And so that's what we're playing calculus Jeopardy with, right? And we know that our formula for that is u to the n plus 1 over n plus 1 plus c, right? So the antiderivative of x squared is what?
X cubed over 3.
Okay, and that makes sense, doesn't it? Because if I were to differentiate x cubed, I'm gonna take the 3 out front, it's gonna cancel with the 1/3, and I get an x squared. So it all works out. So we end up with x cubed over 3 plus, I'm gonna call it c1, some constant. Okay? Okay, so we want to know the value of that constant. So what can we do?
F prime of 0 equals 8.
Okay, everybody see that? Okay, we've got this initial condition. We can call, now, a lot of books are going to say anything they give you is an initial condition, right? And I talked about this last week. You know, I'm a physicist more than a mathematician, and so for me it's very specific. When you talk about an initial condition, that's when you're plugging in 0 into something. If you're not plugging in 0, technically what you're doing is you're finding a particular condition, but it's not initial because the time is not 0. Right? In physics, like 99 times out of 100, when we're looking at a function, it's a function of time, right? It's almost always a function of time. So what's that mean? So that tells us that when I plug 0 in for x, the value of the derivative is equal to 8, right? So if I plug that in, I'm getting 8 equals 0 cubed over 3 plus c1. Okay, well 0 cubed over 3 is just 0, right? So what's the value of c1? 8. Okay. Okay, good. So we can plug that value in up there. And now we end up with the solution here, right? F prime of x is equal to x cubed over 3 plus 8. There's our specific, our particular solution, right? Okay, but we want to keep going, right? We want the value of the function, right? So what's going to be, there's our differential equation. How am I going to solve, and don't say it out loud. I want you guys to think about this for a second. It's a rhetorical question. So how am I going to solve for f of x, if that's f prime of x? Right? So what do you think? Somebody different. Give me an answer. What do you think? Oh, no?
No idea.
You missed, I know you missed last time. Same thing, right? Same thing, we're going to play calculus Jeopardy again. If I want to undo that derivative, then f of x is going to be the antiderivative of f prime of x, right? So our notation, remember, is we're just going to do, so we're going to do antiderivative of all that stuff. Right, and you missed out. Yeah. So you'll catch on. There's a bunch of rules. You got that thing I gave you, right? So if you look on the integral side, it's giving you a bunch of standard forms. And I'll just remind you guys that for every derivative we get, every derivative standard form we have, we can always convert those into an integral, an antiderivative standard form. And we'll do one in a second just to remind you how we do that process. Okay? But the other way to think about it, so we're gonna come up with these standard forms that we can always look at the sheet, we'll just memorize them. You'll have kind of a working knowledge of these, just a handful, you're not gonna remember a ton of them. But the big ones, the power rules, the basic trig functions, you wanna just know, when you're taking an antiderivative, okay, here's the template I always follow. But don't lose sight of the fact that when you're taking an antiderivative, you really are playing calculus Jeopardy. You're just asking yourself, the derivative of what is that? See what I'm saying? So it's always going to end up being, you're always kind of working backwards. You're reversing the process that you've been practicing all year when you do an antiderivative. That's all essentially you're doing, right? Okay, so then, whatever the first derivative is equal to, that's what we want to anti-differentiate. Okay, so now we gotta go again. So the antiderivative of x cubed over 3 plus 8. But remember from last time that one really convenient thing about this, and it makes sense. You think about this, the differentiation and anti-differentiation are linked strongly, right? There's kind of, depending which way you go, are you differentiating or anti-differentiating, you start with one and go to the other. Remember the technique we had, you still have, for taking derivatives. If I have a whole bunch of terms, we can differentiate term by term, which makes things a lot easier. Just take things in small pieces, which stands to reason when we reverse that process, we can do the same thing, right? So we can break this integral up into two simpler integrals, right? And we can just do each of them separately. So what's that going to give us then? So what's the antiderivative of x cubed over 3? Yes, sir.
X to the fourth over 12.
It is. It's x to the 4th over 12. Good. We've got this 1/3 out front. Very good. So we get this 1/3 out front. There's our 1/3. And then the antiderivative of x cubed is going to be x to the 4th over 4. So the 1/3 is a constant. We always just pull the constants out front, but you can combine them. In a case like this, you just know you're going to get 12 on the bottom, right? So that's what I get from the first term, plus, what's the antiderivative of 8? 8x. There you go. And then I'm going to have to include with that, of course, some other constant. Call it C2 this time. Okay? So we get our general solution, f of x equals x to the 4th over 12 plus 8x plus C2. But now we've got our other initial condition, which is an initial condition for the function. F of 0 equals 4, right? So this guy. If we know f of 0 equals 4, we can plug that information in and find C2, right? So we know f of 0, if I plug 0 in, I'm getting 4, I'm plugging in 0. And so this works out pretty well. Both of these terms vanish to 0, and what's the value of C2? 4. And our final answer then just looks like f of x equals x to the 4th over 12 plus 8x plus 4. Okay? Make sense? Okay? So we can do some cool stuff with this concept. What about a differential equation like this that means something? So we've got an evergreen nursery usually sells a certain shrub after 6 years of growth and shaping. The growth rate during those 6 years is approximated by that function. Okay? So that's a differential equation, right? The derivative of h with respect to t is this. Another way of writing that would just be h prime of t. Okay? So how can I solve that? You can probably jump right to the antiderivative. What's going to have to go? What's going to have to go in there? Good. Okay. It's It's gonna be the derivative function, right? We're trying to undo the derivative function, and so it's gonna be this stuff. Okay, but for Eldon's benefit, and just as a quick reminder, how can we get there? How can we get there without just making that jump? I mean, that's a pretty easy jump to make, and you don't have to justify your answer. But all we'd have to do, if I wanted to kind of show the algebra steps that we use to get there, first of all, I'm gonna multiply each side by dt, which puts this in what we call differential form. And then remember, we're just gonna undo the derivative by integrating both sides, anti-differentiating. And we know that the antiderivative of a derivative cancels, and so we get h equals all this stuff. Right? And now we have to just solve that integral, and that's what we're in the process of doing. Okay, so what do we get then? What's the antiderivative of 1.5 times t? We'll pull the 1.5 out front. What's the antiderivative of t dt?
T squared over 2.
T squared over 2. Okay. So we can... Okay. Plus, what's the antiderivative of 5 dt? 5t, good. And then I have to have a constant there, right? So there's my general solution. So what do we get? 1.5, that's 3 halves over 2, so 3/4. 3/4 t squared plus 5t. Now what do they tell us here? They tell us anything specific?
T equals 0, I guess h is 12.
Okay, so if we're measuring height in centimeters, which it looks like we are, this represents an initial condition, doesn't it? Isn't that the same thing as saying h of 0 equals 12? Right? So we can plug that stuff in. This is our, remember, this is what h of t is. And so if we plug in that initial condition, that gives us 12 equals 3/4 times 0 squared plus 5 times 0 plus c, so c is 12, right? In that case. And if c is 12, then we can plug that in right there and we got our answer. And then we can just use that to, it's just algebra to find the rest of this stuff, right? So the height after t years is our function, h of t. And how tall are the shrubs when they're sold? So after 6 years, we would just plug in whatever we get. H of 6 is going to be 3/4 times 36 plus 30 plus 12. So what do we get? 29, 57, 69. Is that right? 69 centimeters. If I added those up right, I don't know if I did.
Yeah.
Right? Okay. All right, so we can do something really cool with this, right? So now, this is where you kind of start to make a strong connection between, we've already talked about the graphs of the kinematic functions earlier in the year. You kind of get a good idea with differential calculus. You know that if you have a position function, velocity is the derivative of position with respect to time, acceleration is the derivative of velocity with respect to time. Okay, but how do you come up with all those kinematics equations? It's pretty simple. All you have to do, if you want to come up with the kinematics equations on any planet, any place where gravity is relatively constant, here's all you have to do. So if we say, if we're starting off with the definition that that, we'll write it in this form. So S is position, V equals velocity, and A equals acceleration. Okay. So then we know that A of t equals V prime of t, which is S double prime of t, right? So let's say we know that A is some constant, acceleration is some constant. Okay. So we want to come up with some equation that relates velocity and acceleration. Well, here's our relationship right there. Okay, we know that V prime of t equals A, right? So if I want to solve for V, I've got to solve that differential equation. That is a differential equation. It's got a derivative, so I have to undo the derivative, right? And so what's that tell us then? Okay, so we know we're going to take an antiderivative of something, and the variable is dt. And what goes there is whatever the derivative of velocity is equal to, right? So that's got to be, if it's in there, it has got to be v prime of t, which is a. Okay? It's a pretty easy differential equation to solve. What's the antiderivative of some constant a? What do you get?
A t equals c.
So you get AT, right? And then within a constant, we've got to always add our constant of integration. So we end up with V of t equals A t plus, let's call it C1. Does that make sense? I mean, it could have been an 8, could have been a pi, it's just some constant, right? So we get, and if you look on your, this one shows up on there, probably the first one. So the derivative, or the antiderivative of some, actually that one didn't show up on there.
You have number 3.
Yeah, so I mean, I guess it's a combination of number one. If we want to add specifically, we can do this, right? We can say the antiderivative of A du is just AU plus C. Okay, but you guys already know that, right? What would you differentiate to get A back? Well, A times T, okay? We got to find the value of C1 though. Well, what could that be? I didn't give you any specific conditions here, anything, any ideas? What does that represent? I didn't give you any specific information. We didn't really start. It wasn't appropriate, right? We didn't start with any. I didn't give you a specific situation. All I told you was acceleration is constant. So can you think of what a possible meaning of that constant could be then? Okay, but we're not going to be able to pin it down to a, to like a number, not a specific answer. Well, acceleration's A, it's constant. But what do you think? I mean, is there anything you could think of that might be a smart number to plug into that equation? The 0 might be good, right? If I plug 0 into velocity, that means that's initial velocity, isn't it? I want to know what is the velocity when t is equal to 0. That might be, well, if you're in physics, you've seen it. That's an important kinematic quantity. What's the initial velocity of an object, right? So if we plug in 0, we end up with v of 0 equals a times 0 plus c1. Well, a times 0 is 0, right? And so the meaning of c sub 1 is v at time 0, but we have a specific notation for that in physics. We just call it v naught, v sub 0, right? Which means initial velocity, okay? So that's the meaning of that constant. So we get that's an important answer, right? We end up with the answer v, velocity is a function of time, is equal to, we'll turn it around, so that goes first. Initial velocity plus at, right? If acceleration is constant. I bet you've seen that before, right? Okay. So there's a kinematics equation, an important one. Okay, and all that is the solution to a simple first order differential equation, right? Okay, so now we want to go one step further. Let's find position. Well, we know velocity is just the derivative of position, right? So, okay, so if we know that s prime of t equals v naught plus at, yes, sir?
Would position be the same as displacement?
No, it's not. But we'll show you how to turn this into displacement at the end. You can write all these kinematics. This is more if you're a physics type. If you're in a physics class, then this is. Otherwise, some of this might seem a little bit odd. You haven't probably talked about these quantities as much. But it'll just take a second. I want to do this for all the. I mean, it's good to see, because if you're not taking physics now, you're almost certainly going to take physics in college, right? So then this is going to lead us to the solution. We got to solve this differential equation. So if I want to undo the derivative, if the derivative of position is this, then position must be the antiderivative of all that stuff, right? So all this stuff right here becomes the integrand. That's what we're playing calculus Jeopardy with. Okay, so what's that going to give us then? So s of t equals, what's the antiderivative of v naught? Now, is v naught a variable or a constant? It's a constant, right? It's a constant. It was the value of our constant. Okay?
Yeah.
It's just that we have some object that's in motion, and it's going to be a constant describing how fast was it going at the start of our video, right? So what's the antiderivative of v naught?
V naught t.
Okay. Derivative or the antiderivative of a constant is the constant times t or x or whatever our variable of integration is. Okay, how about this one now? Don't say it out loud. What's this one going to be? I've got a as a constant, right? So that's out front. What's the antiderivative of t to the 1? T squared over 2, right? Okay, so that if I combine those, isn't that going to give us a t squared over 2 plus some other constant, we'll call it c2. Okay? All right, so there's our solution, but we want to try to establish what's the identity of that other constant. We'll play the same trick, right? What do you think?
S naught.
S naught. Yeah, we'll plug in 0 again, right? If we plug in 0 for t, we get s of 0, which is the same thing as s naught. Not snot, it's s naught, they're different. Equals v naught t plus 1/2 at squared, we could call that, plus, oops, all right, I want to plug in zeros there, my mistake. And if I evaluate that at 0, each one of those terms goes away, right? And so I'm left with C2 equals S of 0, which is the same thing as saying S naught, right? And so now if we rewrite that, if we plug that value in, look what we get. We get the other kinematic equation. S of t equals S naught plus V naught t plus 1/2 at squared. Okay, you might have seen that. Okay, now if you want to write that as displacement, which I think your books do, right?
Yeah, then you just subtract S naught on each side.
Yeah, exactly. Yeah, so displacement, delta S, is just a change in position, right? So that's going to be final position minus, I should probably put vector hats on these, minus S naught. So if I just subtract S naught from both sides, I would get S minus S naught equals V naught T plus 1/2 AT squared, and there's your displacement. So delta S equals V naught T plus 1/2 AT squared. That ought to look pretty familiar, right? Okay. And all the other kinematics equations, you can just get algebraically from those. Like you guys do, probably you do the final speed squared minus initial speed squared is 2a delta x or 2a delta s. That's just algebra.
Yeah.
There's nothing to do. You don't have to do any calculus at all. That's just algebra. Okay. All right. So the next step then. So that gets us through antiderivatives. Now, here's where calculus takes a really unexpected turn. So we're going to start, it seems like we're just going in a completely opposite direction, but I promise you it's all going to come together soon. You'll see why I did this. And it's just miraculous that it does come back together. But we're going to look at a different topic completely. We want to look at finding areas under curves, which seems like a really odd thing to do. But in being as we're talking physics, I'll justify it with a little physics explanation. Okay, in physics, what's the definition of work in physics?
Force and displacement.
Okay, force times displacement.
Yes.
Okay, but if you guys are just doing algebra-based physics, and so you're always making the ridiculous assumption that force is constant, right? Force is almost never constant in real life. You hit a baseball. If you look at slow motion at a baseball being hit with a bat, and it's just amazing, that baseball flattens out. I mean, it just completely deforms. And so you get this strong elastic reformation force, right? The ball is deformed and it wants to reform, and so it springs off the bat, right? But as you might expect, the force of reformation of the ball, right, when it wants to reform, it's not linear, right? The more you squish the ball, the stronger the force. So when you first make contact with the bat, there's really not that much force acting on it. It's not until you get that thing really squished that it wants to jump off the bat. And then as it reforms, the force rapidly declines, and once it leaves the bat, it's zero. So it looks, this is pretty idealized, but it would look something more like this, where you're going to get some peak force where the baseball is maximally deformed. And then it's just going to lead up to that, gradually increasing, and after that it's going to decrease, right? And so the realistic goal in physics would be, if you want to find the area under that, if you want to find the work, what you're actually looking at is you're trying to find the area under this curve, right? Because think what that means in physics. If you're trying to find, you told me already that work equals force times displacement, right? Well, force times displacement, that's an area in force displacement space, right? So whenever you're doing a product of something in physics, you can always think about the graph of the area formed when you put those two quantities on opposite axes, on the x and y axes, okay? So it's really nice and convenient if your force is constant, right? Then it's just a product. But it's not so convenient if it's not a constant force. So we got to come up with a method here, and that's the job of integral calculus, and we're not going to finish it this year. I mean, it's something you'll do a lot more of this in college. But we want to at least get to a point where we can start to have an intelligent conversation about how do we go about doing this, right? How can we find areas under curves using calculus? And that's really all we're going to do for the rest of the year, is just try to come up with a way of doing this and practicing it, okay? So we're out of here in like 9 minutes, right?
Yeah.
Okay. So we're not going to jump into too much today, but I want to at least get you thinking about an appropriate method for this, right? So finding an area under a curve is similar to what people first did when they tried to find an area of a circle. Finding an area of a circle is very difficult to do, right? There is not a convenient geometric formula that's going to give us the area. We have it now, but people didn't have it originally. It relies on this weird number called pi that nobody knew anything about, right? So how'd they do it? Well, the geometrists going, way back when in ancient Greece, they knew how to calculate areas of lots of shapes that had straight sides. They managed to figure all, they're smart guys, they figured all that out. So if we were going to maybe try to approximate the area of a circle with squares, can you think of a way you could maybe get a rough approximation of the area of a circle with squares?
Squares on the outside and squares on the inside.
Squares on the outside and squares on the inside, right? We could pick the biggest square, the biggest square that fits inside the circle. So we would call that the largest inscribed square. So we're gonna inflate a square from the inside until it bumps into the circle, right? And then we're also gonna calculate, the smallest circumscribed square. And somewhere in between is gonna be the area of the circle, right? So what do you think might be a reasonable estimate then?
You guess that half is of the area in between those two squares is.
So we could just average the two?
Yeah.
Okay, it turns out that's not bad. It's gonna get us fairly close, but it's not gonna be the answer, because it's not a linear relationship, right? But it's close. Gets us reasonably close. I wanna do better though, right? So if I wanna do better,
Add more shapes.
I could pick different shapes, right? You can already start to see if I just go from a square, which is a regular four-sided shape. Oh, darn it, we'll do that. That. Oh, we'll do that. So let's get rid of these, let's ditch the squares. And let's try it with something else. Okay, let's try it with hexagons. So you can already see that if I inscribe a hexagon and I circumscribe a hexagon, it's a lot better, isn't it? Right? It's not by no means perfect, but it's a lot better than it was with the squares. There's not as much extra area that's being wasted there, right? And so you can kind of come up with an idea then. Obviously, if we want to get closer and closer and closer, what's our strategy?
Add more sides.
Add more sides, right? The more sides in our regular polygon, the closer we get. What's the only way we could ever get an exact answer?
More sides.
Okay, yeah, if we take an infinite-sided polygon, which of course we can't do, but that's why we have limits, right? So we could take the limit of an n-sided polygon as n goes to infinity. So you really could, and it's a good model in some ways, you could describe a circle as a regular infinigon. It's really what it is. I mean, and you would, if you did that, would you agree that the outer n-gon would start to shrink down, its area would shrink down, and the inscribed n-gon would grow, and eventually they would meet at one answer if we let the number of sides go to infinity. Okay? So then our goal is, we want to apply that thinking to an area under a curve. So here's our project for tomorrow. Our project for tomorrow is we want to try to come up with the area under the function f of x equals x squared on the interval from x equals 1 to x equals 4, right? So the area just would look like that. That's the area we want to find, okay? We got to think of a way we can do that. Okay, we got to think of a way we can apply the same kind of thinking to an area under a curve. Okay, any just preliminary suggestions with this?
Let's use a triangle.
Okay, we can do a series of any kind of shapes we want to. We could make them into triangles, right? We can do anything we want, and we could pack a bunch of those maybe inside and a bunch outside, okay? But we want to do this in a way, now here's where we want to be tricky about this, and the answer is, it's really elegant and simple. But we want to do this in a way where we could easily increase the number of shapes to vary how accurate we want to be. Get the idea? Okay. Do you have a suggestion?
I was gonna say.
Same thing, triangles, okay. So how about if we did something like this? How about, just not because these are the best possible shapes, but because they're easy to calculate areas, right? How about if we pick something like rectangles? Okay, so what if we were gonna take Get that up there. Now, what I've done here, this isn't, all I'm saying is if I partition off a certain range of x values, right? So I'm gonna go from, I'm gonna call it x sub 0 up to x sub 1. And then I do the same thing again. So I'm gonna partition off another range of x values. And from those ranges of x values, I'm just going to, I'm gonna cheat a little bit. I'm just gonna define some rectangles. Let me just put these in place real quick. To make the process simple, let's just say that we're gonna make all of the regions the same. So the rectangles we're gonna build, let's say they all have the same width, right? But the rectangles are gonna be determined by just the height of the function. So for example, if I wanna build rectangles that are circumscribed rectangles, so I'm gonna start down here at x equals 0, and I'm just gonna push these things up until they are, actually I'm gonna start way up here, and I'm gonna deflate them and shrink them down until they bump into the function, right? So the area of the function between these two x values is gonna be approximated by the area of that rectangle. Now, it's not perfect, right? The rectangle is a little bit too big in this case. But I could do the same thing for each of these intervals we're gonna talk about, right? So I could go from, we might set that to be, the widths of our intervals could be 1/4, or they could be 1/2, or they could be 1. We can arbitrarily set them to be whatever we want them to be, right? The smaller they are, you can probably already see, the better they're gonna fit the area under the curve, okay? To be continued.
Mr. Oyas?
Yes.
Anything on it? So, the assignments you put up, they're